Yeah, thank you for the opportunity to speak here. I'm not yet a doctor or researcher, and I'm going to talk to you about a compact OPM-MEG system. And conventionally, MEG has been conducted in these large MSRs, magnetically shielded rooms, and naturally, when OPMs have become a viable alternative, they have also been used in these sensors. However, due to their small size, compact shield, which is more cost-effective and can be fitted in many more spaces, is a viable option, and other groups have built these kinds of systems. But our system, we have these design goals. So for a more conventional setup, where you have a static subject in a supine position, a small footprint for the whole shield, but still having a spacious volume inside for the subject, and then easy operation of the subject by having a non-magnetic sliding bed and adjustable sensor mounting, and then also using active shielding and magnetic OPM calibration. So these are the goals. Then what we ended up with was we designed, together with the shield manufacturer Vacuum Smelts, this shield, which has two mu metal layers with an aluminum layer in between. The dry weight is 1 metric ton. The size is 2.4 meters by 1.4 meters, 1.4 meters, so quite small, but still you have a cross section of 1 times 1 meters inside for the subject, and the target volume for the optimal shielding is a 20 centimeter radius sphere, 40 centimeters from the back of the wall. And in the picture, you can see the non-magnetic sliding bed with the OPM helmet mounted to it, and the electronics rack and computer for the OPM control and data acquisition. And the OPM mount is a 3D printed helmet with sockets, 99 sockets glued onto it, which have adjustable sensor depth, so you can, with friction, put at any distance the sensors so it touches the head of any shaped subject. And this is what it looks like when you have had a subject inside. So you have a cushioning for the head of the subject, some fastening screws from the side to support the head, so you are stationary, and then you can just push the sensors right against the scalp with some thermally isolating swim cap. Then, unfortunately, this is still in progress work, so we haven't yet used the coils we are meant to do. So we aren't even degaussing the coils. It works, but we lack the coil driver. And then, like in the last presentation, we are in the design process of designing PCB coils to be placed inside. But it's a bit more tricky because when you place it close to the shield walls, of course, you have to consider all the effects the shield has on the magnetic field. And thus, this work doesn't have yet the active compensation, and the calibration is not done, but for the benefit of source localization in MEG, we instead use the optical co-registration. And this is as simple as having the CAD file of the helmet, measuring the depth of the sensor, and noting down what slot you have. Then you know where the sensor is in relation to the helmet, and then you take a scan of the subject with the helmet, and you have a MRI of the subject also. So then you can align all these geometries together, meaning you know where the sensors are in relation to the brain of the subject. Then for some measured performance of the shield, so we measure the shielding factor along the longitudinal axis and transversal to the shield in the target volume, and this shielding factor agrees with simulations, and as expected, the longitudinal shielding is worse as we have always open foot end in our shield. Then we also measured the remnant DC field in the target volume. And note this is not the Gauss shield, but still pretty good. We measured it with flux gates. So in the center of the target volume, we had 5 to 10 nanotesla field, and in the whole target volume, we had a field below 20 nanotesla. So the internal coils of commercial OPMs have easy time to operate in this, but the additional coils and the Gaussing should bring this closer to zero field in the target volume. We also looked at the thermal magnetic noise, starting with an infinite plane to model one of the shield walls. We did some measurement at different distances from one of the walls, adjusted the model, just scaling it linearly, and then extrapolating it to consider all the walls around it, again with infinite plates. So in the target volume, the thermal noise is at most 4 femtotesla per root hertz, so no worries there. And then we looked also at the vibration modes in the shield, and these we only have a stiffening aluminum I-beam inside the shield, so there is still room for improvement. But here we have 14 Q-spin OPM channels averaged, the PSD averaged, so then we can see when not perturbing, we have mainly 26 and 38 hertz peaks, and these are raised when perturbing the floor. So these two components seems to be coming from the room, and perturbing the floor, bed, and walls, we get some sub 20 hertz vibration modes. Then next we place the subject inside the shield, and the blue and yellow line are raw data of without and with the subject inside the shield. And you can see that the vibration modes and power line noise dominate the spectrum. So then we process the data for the green and red lines, and so notch filtering and signal space projections to target the vibration mode artifacts. So then you can nicely see afterwards the difference from adding the subject, that you can see raising power in the band below 35 hertz, which is expected. Then we also did some MEG experiment doing the well-studied medium nerve stimulation paradigm, where we stimulate the left median nerve of the subject, so getting which then induces a somatosensory response in the right hemisphere. So then we had 7 dual-axis OPMs placed over the somatosensory cortex to measure this response. And when epoching around the given pulses, and this is also the same processing I mentioned before, and then baseline normalizing, we get this nice responses of N20 and P35 at expected, and these have also like expected topographical maps. So this sensor space field pattern is quite dipolar, and then we, due to the dipolar nature of the field, we use an equivalent current dipole fit to estimate the source location. And here in the picture to the right, you can see the red arrows. They represent the sensitive axis of the OPM, and then we have the expected source location in the cyan sphere. So this is the post-central gyrus. So we didn't quite manage to place it, the estimated dipoles in the expected location. So one gyrus posterior to the expected one. But then when we used another source estimation approach, so minimum normal estimation, we got the peak activity in the correct location. So this can be chalked up to a low number of channels and potentially non-ideal sensor placement for capturing the field pattern at the sensors. And we also looked at some beta rebound, so induced responses. And here we can see clearly at 16 Hertz, the expected beta rebound. But then we also saw in a subset of channels some rebound also at 35 Hertz, which we are not exactly sure what it is. So I won't say anything. And discussions and conclusions. We met most of our goals for the system, but this work is still ongoing, so we haven't yet involved the coils in the system. Therefore, improvements mainly involve them, so degaussing the shield, dampening vibration modes, adding electromagnetic coils, and adding more sensors. And to conclude this work, this presentation, so our compact OPM-MEG system enabled us to perform a high-quality MEG experiment in an office environment. The planned improvements will further increase the quality of the OPM data. There are some citations in the slides and funding. And the last line of funding is from the OPM-MEG project. So there's a website for us, and here you can see the partners. And that's all for me. Thank you.
Thank you.